Okay, good afternoon, everyone. My name is John Dale, but most people call me JD. And for the next 5 minutes or so, let me reel you in the very interesting and important field in geosciences. Now, living in the Philippines has shaped my appreciation for sciences, especially in how it can make an impact to society. Our geographic location and tectonic setting has led us to experience so many disasters and exposure to a lot of natural hazards that we rank #1 in many of these kinds of rankings. And also, as an ambitious young geologist, why not study and specialize in one of the most unpredictable phenomena, earthquakes? Now, earthquakes are a manifestation of how stress gets accumulated and released in the Earth's crust in pre-existing fractures, primarily due to the tectonic plates colliding and sliding against each other. Now, and if you have a fault on a landmass, if you built a road across such an active fault, like the San Andreas Fault in California, the movement of the tectonic plates in opposite directions will cause the road to deform slowly and gradually over tens, hundreds, or sometimes thousands of years. But the two tectonic blocks are locked together by friction along this fault plane, which is a three-dimensional plane. And thus, stress is accumulated over time. We call this period the interseismic. And just like when you pull an elastic band, at some point, that fault will snap and release the stress in the form of an earthquake. This stress accumulated over a long time will be released in a few seconds, maybe a couple of minutes, radiating seismic waves that then cause the ground to move. The friction eventually recovers and the fault accumulates stress once again. And this brings us to this concept of the earthquake cycle. This process will go on for as long as tectonic plates are shifting. The highly simplified diagram at the bottom highlights the general cyclicity of this process, wherein every time the stress on the fault reaches a breaking point, essentially dictated by the friction on the fault plane, it will fail in an earthquake and then start building up stress again. Typically, we use GPS to track the movement of the tectonic plates and tectonic blocks. However, these instruments are very expensive, so it's no surprise that many parts of the world do not have such data sets. If you compare the data in Japan, which is virtually covered by all of these velocity vectors you see showing the movement, in the Philippines, we have very few data sets. Thankfully, with satellites, we're able to track the movement of the ground. Specifically, with specialized radar satellites, we point the satellite to the ground and we know the wavelength of the radar signal, and these satellites emit a microwave over a wide area of land. And if you know the wavelength, you know the time it takes for the radar signal to come back, and you can then measure the phase difference if the ground is moved after several passes of the satellite. It's essentially using a basic principle in physics called interferometry. And this technique is what we call as INSAR. From assuming uniform slip-on faults, especially when you have not a lot of data, like with satellite data from INSAR, we can map spatially, much more continuously, the deformation of the ground and create much more discretized models of faults to show us which parts of the faults are slipping aseismically and not accumulating stress, the red areas in this fault model of the San Andreas Fault, and which parts are accumulating stress, the blue areas in this fault model. And these areas are which areas that are producing earthquakes, essentially. And this kind of technology has allowed us to leapfrog information and what we know about earthquakes in the Philippines. So from my work for my PhD a few years ago, we were able to process INSAR data over this island in the Philippines called Leyte, which is cut across by a fault line. And we produced one of the most detailed SIP models for a fault in the Philippines, showing us a part of the fault, or a 20-kilometer long section, which is accumulating stress. And this exact section ruptured in an earthquake. And from these models, we can calculate the balance of accumulation and release, and we can see that the time interval between earthquakes around 22 to 79 years. And through historical seismology, we can see that these estimates seem to make sense. The last earthquake was 70 years ago, and prior to that, it was 57 years. And there's so many more faults across the world that we need to understand and study. All these black lines in this map are faults that we need to study. Many groups are trying to map automatically the data sets. Space agencies, like the European Space Agency, has a ground motion data set for Europe. And in the Philippines, I've been lucky enough to start a project with some funding from our science agency to understand the faults, especially the faults near Manila, which is rapidly urbanizing. And it's a reality that many communities live in hazardous places. So it's these kinds of open data sets, the satellite data from government agencies are free and open to use, that we can make strides in terms of what we know about earthquake potential, especially in the less resourced regions of the world. That ends my presentation. Thank you very much for listening.